So mass percentage is what we'll deal with a little bit next, and these can be easy and they can be hard, and we're going to do the easy version first and the hard one second. So the first question, what is the percentage of sulfur in the sample of H2SO4 that we had right back here? Now it turns out mass percents are an example of an intensive property. What did that mean again?
Intensive, it means that it counts on the number of things that you have.
So actually, yeah, the size of your sample does not matter. So whether we have a 196 gram sample or a 196 million gram sample doesn't matter. The mass percents would work out exactly the same, which means I don't actually have to start with 196 grams of H2SO4. I can choose whatever amount I want to start with, which is convenient because I'm going to choose to start off instead with a 98 gram sample of H2SO4. And why did I choose a 98 gram sample? What's special about that? Good, because that's exactly 1 mole of H2SO4. And because I'm at exactly 1 mole, it's easy for me to figure out exactly how many moles of everything else I have. So, in this case, first question is what is the percent sulfur in the sample? So, and for a percentage, we just want the part over the total times 100. And so in this case, my total for 1 mole sample size is 98 grams. How many of those grams are sulfur? Well, if I have 1 mole of H2SO4 here, how many moles of sulfur? 32. So 1 mole, which is 32 grams. So in this case, 32 grams over 98 times 100. And what is my percent sulfur here?
32.6.
Any more sig figs on that?
Yeah.
Oh, 653. So if we would have left it at 32.6, would we have been off? Because if we want to go to that sig fig right there, we should round it up to 32.7. Only reason I asked. In this case, I'm just going to leave it right here. Say 32.653%. This is probably not a question that's going to be quizzing you on sig figs. Cool. Second part of this is what is the percent oxygen? And in this case, again, in my 98 gram sample size, it's 1 mole. How many moles of oxygen are there? 4. And what does 4 moles of oxygen weigh? Well, each mole weighs, according to the periodic table, 16 grams. So 4 moles would weigh 64 grams times 100. And what do I get for my percent oxygen? 65.3%. 65.3%. I'll leave it at 65.3. Okay. Close enough. Multiple choice test, life is good. So 65.3% oxygen, life is good. So that's the easy way of involving mass percentages in a question. If you already know the formula of your compound, life is good. I don't care what sample size they give you, choose a 1 mole sample size that will make your life a lot easier. The other way this could be asked, instead of starting out with the molecular formula and finding mass percents, you can be given the mass percents and have to find what we call the empirical formula. And this sucks. So let's first talk about what an empirical formula is. So it turns out there's a substance called benzene. So and every single benzene molecule has 6 carbon atoms, 6 hydrogen atoms. The empirical formula is the most reduced whole number ratio of atoms. And what is a more reduced whole number ratio of atoms besides 6 to 6? Yep. CH. And again, that reduced whole number ratio, most reduced whole number ratio, we call, if I can do this correctly, the empirical formula. But exactly how many of each atom exist in an actual molecule, we call the molecular formula. Now, for a lot of compounds, the empirical and molecular are exactly the same. Notice if I have ethanol here, C2H6O, can I get a more reduced whole number ratio than that? Yep. A 2 to 6 to 1 ratio can't be reduced any further and end up with whole numbers. And so the empirical and the molecular are one and the same. So, but for some molecules, the molecular and empirical are not the same. Turns out, if I give you the mass percentages, you can get the empirical formula. You actually can't directly get the molecular formula unless I give you the molar mass. So in the next example, I tell you that a certain substance is 80% carbon by mass and 20% hydrogen by mass. And then the question is, what is its empirical formula? And a lot of times they'll give you a question like this one where the numbers look so nice. And a lot of students look at this and like, oh, I don't even need my calculator for this. Look at that. Fantastic. This is just C4H. Life is good. Is life that good? What does this imply a ratio of? 4 to 1 of what?
4 moles of carbon to 1 mole of...
Good. 4 moles of carbon to 1 mole of hydrogen, or 4 atoms of carbon to 1 atom of hydrogen. I'm going to use the mole-to-mole ratio. But these are not mole percentages. These are mass percentages. So can't get a mole ratio from a mass ratio. It's not the same ratio anyways. You can get it from it, they're just not the same ratio. In this case, can I use a 1 mole sample size like we did in the last problem? Why not?
Well, I mean, you can.
Well, actually I can't, because I don't know the formula. If I don't know the formula, I don't know how much a mole weighs. So actually I can't use a 1 mole sample size. So in this case instead, it is really convenient to use a 100 gram sample size. If I have 100 grams and 80% of those grams are carbon, how many grams of carbon do I have? 80 grams. And again, if I have 100 grams and 20% of those grams are hydrogen, how many grams of hydrogen do I have? 20 grams. So save yourself some math by using a 100 gram sample size in this case. Cool. Now this is still a gram to gram ratio. It's still a 4 gram to 1 gram ratio of carbon to hydrogen, but I don't need a gram to gram ratio. I need a mole to mole ratio. So in this case, what do I need to do?
Take the number off the periodic table.
Yeah, use the molar mass of the periodic table and convert these to moles. So I'll put grams of carbon on the bottom, moles of carbon on top, grams of hydrogen on bottom, moles of hydrogen on top. So which one of these is easier to do?
Why not carbon?
Okay, we'll do carbon first. Hydrogen's really easy because it's 1 to 1, and life is good, and I have 20 moles of hydrogen. So, but for carbon, what's the molar mass for carbon? 1 mole weighs?
1 mole weighs 12.011.
Good, 12.011. As long as they're really close to a whole number, just round it. But if you have something like magnesium where it's 24.3, which is not right next to a whole number, keep the 0.3. So but here I'm just going to round it to 12. And in this case, what's 80 divided by 12?
That would be 6.666.
I'll round it to 6.67 moles of carbon. And now I finally have a mole to mole ratio, and life is good. And my empirical formula is C6.67H20. Fantastic.
Not fantastic.
Why is that not fantastic? I circled it.
Decimal.
Can't have decimals. Oh, now you tell me. Cool, you're right, you can't have decimals. And this answer choice may or may not show up in your multiple choice test, but this is still incorrect regardless. How do I make sure I get whole numbers here?
LCD, I would say.
So,
You can just divide it by 6.67.
good, divide it by whichever number is smallest. So we'll divide both these by 6.67, because this guarantees that I get at least one whole number, a number 1. And in this case, I get C1H 2.998. Since that comes out right next to a whole number, I'll round it. If it didn't come out right near a whole number, I would definitely not round it. So let's say this came out to, instead of 2.998, let's say it came out to 2.5. If it was C1, H 2.5, you would not round this up to 3. How would you make these whole numbers?
Put a 2 in front of the whole thing. So it's
Yeah, double everything. And you get C2H5. So, but we didn't have to worry about that. We just have C1H3, which is the same thing as CH3. And that's our empirical formula. Now, the next question on your handout, though, is what is the molecular formula? This is the most reduced whole number ratio, and that's all your mass percents are ever going to be able to give you. So what are some possible molecular formulas that could, besides CH3, I mean, CH3 could be the molecular formula too, but what are some other possibilities?
C2H6.
C2H6, what else?
C4H12.
C4H12. How about C1000H3000? Notice there's an infinite number of possibilities. Now, if we look at this, CH3, what's the mass of that?
Molar?
Molar mass, yeah.
So 12 plus 3 is
15. And, which means every one of their molar masses has to be a multiple of 15, because we're just doubling or tripling or quadrupling the formula or multiplying it by 1,000 or something like that. So in this case, I know my molar mass is either 15 or a multiple of 15. And if I give you the molar mass, you could then figure out which of these possible empirical formulas really is the molecular formula. I'm sorry, which of these possible molecular formulas is the correct one. So in this case, the next question says, if this compound has a molar mass of 30, what is the molecular formula? Well, what multiple of 15 is 30? Got to double it. And the doubled formula is this guy right here. So that's our molecular formula. Only because we were given that the molar mass was 30. Without that, couldn't have answered this question.